Hello, everybody. Today we will be doing um, molecular geometry. So, we're going to talk about it and then we're going to actually do a couple of practice problems together. After today, you should be able to explain Vesper theory, use structural formulas to describe the molecular geometry, identify the correct geometric name for the shape of the molecule, and identify approximate bond angles for molecules. Molecular shapes. We have learned to draw Lewis structures and account for all of the valence electrons in a molecule. But Lewis structures are two-dimensional, and molecules are three-dimensional. The three-dimensional structure is absolutely critical for the function of molecules. Vesper theory, or valence shell electron pair repulsion theory, states that the electron pairs, both shared and unshared, in the outermost energy level, try to get as far away from each other as possible. So they kind of push against each other. That push, or repulsion, determines the shape of the molecule. We can easily predict the three-dimensional structure of a molecule just by adding up the bonds and lone pairs on the central atom. How we do this is we're going to draw the Lewis structure and then count the number of bonds and lone pairs using the chart to figure out the geometry. Now, there is a reference chart to go along with this, so make sure you either get a copy of that or tell me and I can send you one. Our first example, we're just going to do a couple to show you how this Vesper theory works. So our first example is BeCl2, and we're going to look at this very center atom. When I look at that central atom, there are two lines coming from it, so it has two bonds, and just on the central Be, there are 0 lone pairs. This is a cutout of the chart, so we're going to look and we find two bonds and 0 lone pairs, and it tells us the shape is linear, the bond angle is 180 degrees. I'm going to go ahead and write linear 180 in the box. Next we have NH3, so again find the central atom. That N, looking at the N, how many bonds are there? 1, 2, 3. And lone pairs, there is 1 lone pair. Looking at our reference sheet, we have 3 bonds and 1 lone pair, leads to the shape of trigonal pyramidal with a bond angle of 107.5. Now, it is important that you have a printout of this sheet. That way you can reference it during any tests that we're about to do. Here are all of the shapes that are possible. You have linear, bent, trigonal planar, pyramid, tetrahedral, and trigonal bipyramidal. Now, those aren't all of them, those are just the most common. So, we're going to do some practice. We have H2 to start. So, I have 2 hydrogens times 1 valence electron. So, I'm working with 2 valence electrons or 1 pair. Draw my 2 H's with their single electron. Those 2 are going to pair up. So I have H bonded with H. I wanted to do this one because there is no central atom in H2. Because there's no central atom, we look at whichever the first one is, and there is 1 bond and 0 lone pairs. If we go back, 1 bond and 0 lone pairs is written up here. That gives us a linear shape. With a 180-degree angle. Now for H2O, we're going to do math again. So we have 2 hydrogens times their 1 valence electron, so that's 2. For oxygen, we have 1 oxygen. It has 6 valence electrons, so that's 6. Add them together. We have 8 electrons that we're working with, or 4 pairs. Go ahead and draw which element goes in the center. It can never be H, so we're either looking for the odd man or the one with the most needed bonds. I'm going to put my O in the center. I'm going to draw my valence electrons. I'm going to put one H over here on the left, the other H over here on the right. Start circling. So there's a pair here and a pair here. Now I'm going to redraw with my O in the center, bonded to my 2 H's. On my O, I have 2 unbonded pairs. Now, let's make sure everything's happy and we have 4 pairs used. 1, 2, 3, 4. Check. Each H has 1 line to it. Awesome. And this O has 8 electrons to it. Looking at this O, how many bonds does it have? 2. How many lone pairs does it have? 2. When I look here, 2 and 2 gives us a bent angle with 104.5. For our next example, we have PO3, -3. So, do my math. I have, my P has 5 valence electrons, and there's 1 of those. My O, I have 3 of them, and then each have 6 valence electrons, so that's 18. And then I have the -3 up here, which means plus 3 more electrons. When I add all that together, I get 26 or 13 pairs. Okay. Odd man goes in the center, so I'm going to put my P there in the center. Start drawing its electrons. I happen to have 3 oxygens, so I'm going to place my 3 oxygens on the outside with their 6 electrons around them. Circle where they are going to bond 1 time with each P. Because there's this -3, that means there are 3 random electrons. So they're going to fit 1 on each oxygen to make each oxygen happy. Check to make sure everything's happy, and we use 13 pairs. 1, 2, 3, 4. So oxygen's happy. We're up to 4. 5, 6, 7, 8. This oxygen's happy. We're up to 8. 9, 10, 11, 12. This oxygen's happy. We're up to 12, 13. So we are done. I'm going to redraw that with bonds. Okay. Looking just at my P now. How many bonds does my P have? How many valence unshared electron pairs? So there are 3 bonds on P, 1 unshared pair, 3 and 1 is trigonal plane, pyramidal, 107.5. Next example is CH2O. So we have carbon that has 4 plus 2 times 1, which is our hydrogen, plus 6 for our oxygen. So we have 12 electrons for 6 pairs. If carbon is present, it's generally in the center. Start by drawing our 4 electrons for carbon. Place our 2 H's. 1, 2. Show where those bound. Then we have our O. Our O has 6 valence electrons. So they have to match up twice. Redraw that. The reason I did this as an example is because it has a double bond in it. The double bond is still only counted once. So this carbon has 1, 2, 3 bonds to it, and 0 lone pairs on the carbon. When I look, 3 and 0, trigonal planar, 120. For our last 2 examples, we have CH4 and CO2. CH4, my first C has 4 valence electrons, plus I have my hydrogen, there are 4 of them, times 1. So there are 8 electrons, or 4 pairs, that we're starting with. Carbon goes in the center. My hydrogen, I have 4 of them, so I'm going to put 1 on each side. Circle where they would pair up together, carbon and hydrogen. Check to make sure I have 4 pairs, 1, 2, 3, 4. All of my hydrogens have 1 bond to them. My carbon has 4. Everything's happy. Redraw it with my Lewis structure. When I check bonds and lone pairs, I look at just my central atom. So I have 4 bonds on carbon and 0 lone pairs. That gives me tetrahedral. Which is 109.5. Finally, we have CO2. C has 4 electrons, plus I have 2, and oxygen has 6. So 16 pairs, or 16 electrons, or 8 pairs. Odd man in the center, so carbon still goes in the center. I'm going to draw 4 electrons. I'm going to draw my oxygens on either side. For each oxygen, it has 6 valence electrons. I'm going to start matching them up. Each carbon and oxygen are going to join twice to make everybody happy with full octets. So check to make sure everybody's happy. This oxygen has 4 sets or pairs or bonds. This carbon has 4 bonds. and this oxygen has 4. Redraw it. Now remember, we're looking at the very center, so right here. And double bonds only count as once, so on carbon there are 2 bonds and 0 lone pairs. So it is linear 180 degrees. If you guys watch this video and you are completely confused, please feel free to message me. Have a wonderful evening, and if you need me, I'm here.